Okay, we're ready. So, last class before spring break, let's make it a good one. And it should be, we're going to talk about the mean value theorem. Very important theorem. In fact, we'll use it to actually help us prove the fundamental theorem of calculus. But first, a lemma. So a lemma is just a mathematical fact. That's kind of a little theorem in its own right. It's proven separately, but you kind of use it to help you prove something. And I'm going to use as a lemma to talk about the mean value theorem. How about the Rolle's theorem? Now this theorem says the following. So we're considering a function on an interval, and we know the following three facts. One, f is continuous on the interval. Two, f is differentiable on the open interval. Okay, so when we're talking about differentiable, we can say we can find its derivative everywhere except perhaps at the endpoints. And three, f of a is equal to f of b. So the y values at the endpoints are the same. Okay? And a function like this can have Then, let me just finish the theorem here, okay? So we have a function on a closed interval such that these three conditions are fulfilled. We have continuity on the entire interval. We are differentiable except perhaps at the endpoints. And the y values at the endpoints are the same. Then it turns out there is some c in the open interval. Okay, so there's at least one, such that f prime of c must be 0. A function that behaves in this way will have to have a point inside the interval ab where its derivative will be 0. Okay? So look at some examples here. You could have, for example, a constant function, in which case any value in between a and b will be the same, right? So this is where f of a equals f of b, right? Or you can have something like, here's a, here's b, so it starts here, and then just this ends here. But the thing is, the y values are the same. F of a equals f of b. Now, because it's differentiable ever in the open interval, we know that nothing like a sharp corner is going to happen or anything like that. So it'll be smooth in this kind of way. And you'll realize that, hey, I could pick this point as c. That will have a horizontal tangent line, so my c is there. Or I could have, the function can do essentially anything it wants, but as long as its first y value, f of a, is the same as the second y value, f of b, no matter what it wants to do in the middle, as long as it keeps continuity and it doesn't have any sharp corners, there will be at least one point, for example here, where the derivative will be 0. In this case, we have several such points. Most of the time I have a horizontal tangent line, it means that the derivative is 0. So any function that fulfills these three conditions on a closed interval will have somewhere in the interval at least one place. Perhaps a finite number of places, perhaps even an infinite number of places, but there will be at least one place in which the function will have a derivative of 0. And that is Rolle's theorem. So that's it. Now, why is that true? Assume f on AB has the three mentioned conditions. Okay. So let's pretend we have a function that fulfills those three conditions. There is something that we know then. EVT, this is the extreme value theorem. The extreme value theorem guarantees that we have both a max and min in the interval. Right? Remember the extreme value theorem that says if you have a continuous function on a closed interval, it's guaranteed to attain its absolute max and min on that interval. So any function that fulfills the three conditions, in particular condition 1, the extreme value theorem says we will have to have a max or a min. Both the max and min there. Right? So now there are two cases. Right? We can cover all possibilities in two cases. One, both the max and min occur at the endpoints, or 2, at least one occurs inside. We're guaranteed to have both. They could show up at the endpoints. We've actually looked at that in last class when we were talking about absolute max and mins. Could have both the max and min at the endpoints, or one or the other, or both are inside the interval. Now, I'll leave this picture up here because I'm going to mention it. In one, f must be constant. As you can see from the illustration here. Let's say max and min occur here. Or the max and min occur here. Because this is the maximum, in the interval I can never have any point that has a higher y value. Because it's a minimum, I can't have any point having a lower y value. If the max and mins occur at the endpoints, everyone has to stay at that point, because once someone goes higher or lower, you actually contradict the fact that the max was at the endpoint. So if the max or min is at the endpoint, it has to be a constant function, and in that case, every c in the interval has the property we want. Because no one in here can have a higher or lower y value. And because it's continuous, we have to have points defined everywhere, and so they're all going to have to maintain the same level. They can't exceed or subsede the max or min. So that's case 1, we have what we want. In case 2, W log, see, this means without loss of generality. I'll explain that what that means after I write down the next sentence. Okay, so whenever you see a proof says something like without loss of generality, it means that there are a bunch of cases to consider, but they're pretty much all dealt with exactly the same, so you can kind of substitute one word for the other. So here I'm assuming that there's a max in the interval, but the same proof would work if I replace max with min. Nothing would change, right? So whether there's a max or a min, this argument is going to be true. It smells like something is burning, like something electrical. Or is that just me? It's a weird smell, I just started smelling this now. Hope it's not this computer over here. Anyway, okay, so let's pretend there's a max in the interval. Exactly the same argument will work if there's a min. Because we have another theorem that talks about that. Then Fermat's theorem. Or let's say it occurs at C. Then Fermat's theorem tells us f prime of C equals 0. And that's the end of the proof. So Fermat's theorem was that theorem that says if we have a function that has a maximum or minimum and the derivative exists at that maximum or minimum, which is condition 2, then the derivative at that maximum or minimum will be 0. That was Fermat's theorem. So you'll see in either case, we end up finding a point where the derivative is 0. So it means once those three conditions are fulfilled, we will have a point in the interval, at least one, perhaps infinitely many, where the derivative is 0. We'll do some examples for Rolle's theorem specifically, but since we're in proof mode, let's just continue. Let's actually go with the mean value theorem. The mean value theorem generalizes this idea. And technically, you can apply the mean value theorem to a problem where in the special case, it'll actually give you Rolle's theorem. The mean value theorem makes one less assumption, and it gives you a slightly different conclusion. So here is what it says. Again, let's assume it's continuous on the interval. And 2, f is differentiable on the open interval. Means its derivative will exist at all points inside. No other assumption is made. Then, right, so we're not making the third assumption. There is a value C in AB such that f prime of C is going to be f of b minus f of a over b minus a. Now that formula you'll note or remember that it is the formula for the average rate of change. We also saw that the derivative can be thought of as the instantaneous rate of change. So the mean value theorem asserts that there is some point in the interval where your average speed and your instantaneous speed are the same. Once those two conditions are fulfilled. Let's look at some illustrations of that. So this can actually be a Rolle's theorem case. That will work. But let's say you have something else. Let me use first two as the Rolle's theorem case as well. Because I am going to make the argument that the Rolle's theorem case is covered by this. That's this. So in both those cases, your f of b equals your f of a. But this doesn't need that assumption. I could make it different. Let's say my f of a is here. And my f of b is here. Something like that. So the mean value theorem asserts that at some point inside the interval, the instantaneous rate of change is equal to the average rate of change. Notice that in both of these cases, your f of b minus f of a over b minus a will be 0 because f of b and f of a are the same. Right? Same thing here. So pretty much any point I pick here, the derivative at that point will be the same as average rate of change. For this one, again, I can pick this point. At that point, f prime is equal to 0, which happens to be the same as f of b minus f of a. In other situations where your f of b is not the same, pretty much your f of b minus f of a is going to be the slope of this line. Right? Slope here equals f of b minus f of a over b minus a. The mean value theorem says there's a point where the instantaneous rate of change will have the same slope. In this case, I can pick, say, this point. The tangent line there is parallel. It should be parallel, not on to scale. Okay. There is some point in the interval where the tangent line is parallel to the secant line. They will have the same rate of change. And I'll always be able to do that. So I can connect these 2 points. The secant line is the line connecting the endpoints. So the slope here is equal to f of b minus f of a over b minus a. There has to be some point inside this interval where the derivative, the slope of the tangent line is the same. So for example, I can pick one here. There's also another one here. But I only care about at least one. Here, f prime of c equals average rate of change. So a common kind of real-world example to talk about here is let's say you're driving from point A to point B, and they're 80 miles apart, and you make that trip in an hour, then the mean value theorem says at some point during that trip you would have had to have been traveling at 80 miles an hour. That's what the mean value theorem would say. Sure, you might stop at a stoplight, you might slow down, you might speed up, but there's going to be some point in that trip where you hit 80 miles an hour, right? And you would never be able to make the trip in an hour if you didn't do that. If you're always driving slower than 80 miles an hour, you would have taken longer than an hour to get there. If you're always faster than 80 miles an hour, you take less than an hour to get there. There had to have been some point where you were in the middle, where you were at 80 miles an hour. Okay? So you might speed up or slow down, but ultimately there's always going to be a situation in the middle where the average rate of change is the same as the instantaneous rate of change. And that is the assertion of the mean value theorem. Once you have a function that's continuous and on a closed interval, differentiable on the open interval, then the instantaneous rate of change is equal to the mean rate of change at some point, and so that's called the mean value theorem. Right? Mean is just another word for, it describes a particular average, this kind of average. Now, why is that true? Now, this is going to be one of those magic proofs. I mean, if you think about it a little, you can kind of see where this comes from. But one of those magic proofs in mathematics is when someone proves something by just giving you some example and say, hey, check this out. And then you're like, where did you get that from? And then they proved what they were talking about. Like, where did that come from? It's like you pulled something out of a hat, right? So here's the idea. Let f of x have the two properties mentioned. And here's where the magic comes in. Consider. It's the most scary word in mathematics. Every time someone says consider in a proof, you know that something's coming. Like, consider what? What now? What are you going to do? Consider this function. Okay. All right, so one way you can start to think about this is that this is kind of the slope of the tangent line, except it doesn't have that limit. Like, once you put the limit in front of here, this is going to be the slope of the tangent line times x minus a. So this is almost the slope of the tangent line here. And so he's measuring the difference between the function and the tangent line. So the idea is measuring the average of this. At some point, those will be the same, so you look at a difference. And ultimately, you kind of want to show that that difference is going to go to 0 at some point. Okay, so that's kind of the explanation here. But a lot of times, whenever someone says this, they're going to tell you some function where you're like, you have no idea how they came up with it. But yeah, so suppose we have f of x having those two properties. We construct this new function g. Now, g has the same properties. So I constructed g by just adding and multiplying continuous functions, and we have that theorem that says you will maintain continuity by doing these regular arithmetic operations. So as long as your a and b are not the same, so you're not dividing by 0, we're fine here. And g will have the same properties, it will be continuous, and it will be differentiable. Your f of b minus f of a over b minus a is just a constant. It's going to be whatever the average rate of change is. Note, look at what g of a is. Well, that's going to be f of a minus f of b minus f of a over b minus a times a minus a. That's therefore going to go to 0. So your g of a equals f of a. Also, look at what g of b is. Well, that will be f of b minus f of b minus f of a over b minus a times, now I'm going to plug in b for x. That's going to cancel this. And if I take f of b minus this, I'll have f of b minus f of b minus f of a, gives you positive f of a. So then I get g of b equals f of a. So you have g of a equals g of b. Now that's nice because now we can use Rolle's theorem. We have a function that's continuous on a closed interval, differentiable on an open interval, and now I know the function I'm looking at has the endpoints giving the same y value. By Rolle's theorem, there is some c so that g prime of c equals 0. But clearly here g prime of c is just going to be the derivative of this function evaluated at c. That's going to be f prime of c minus, well, this is just a linear function. The derivative is just going to be the derivative of this times the constant factor rule. Derivative of here is 1, so you'd end up with just this guy. And we know that this is equal to 0 by Rolle's theorem. And so now what you can do is just move this to the other side. And that is the proof. With these two conditions, there will always be a point in the interval where the average rate of change is the same as the instantaneous rate of change. Or should probably state that vice versa. And that's the mean value theorem. As I said, very important theorem. We are going to use it again to prove other things. However, you will be tested on this specific theorem in and of itself. Let's do some examples. I'll do some for Rolle's theorem as well as the mean value theorem. But technically, you can see that the mean value theorem will include Rolle's theorem inside of it, because in the event that my f of b and my f of a are the same, this gives me 0. Where are my examples for course? example. Mean value theorem, I'm going to just abbreviate that as MVT and consider this function. And again, I might follow up, especially on a test, I might follow up with a question like, how do you know? And to answer such a question, all you do is just list off the 3 conditions that this function would fulfill, and then say, therefore, by Rolle's theorem, I know my answer is the right one. Something here. How do you know? Okay, so what you would do here is find f of 0. Boom, boom, boom. That'll be 2. Find f of 1. That'll be 1 minus 3, which is minus 2, plus 2, which is 0, plus 2, which is 2. So then you'd say, oh, f of 0 is equal to f of 1. This is a polynomial, so it's definitely continuous everywhere. So in particular, it's continuous here, and it's definitely differentiable everywhere, so it's definitely differentiable on the open interval. Therefore, I know this is true, right? You just go through the statement of the theorem. So a question like that is pretty much going to test you on whether you actually know what the theorem says, and you're expected to know what the theorem says. I might even put a problem on it that asks you to state the theorem. So just be prepared for that. All that being said, we know these two are polynomials, so they satisfy everything. And I just proved to you here that the endpoints give you the same y value. Here we don't care about that condition. So now let's just actually go through the computations of finding that guy. So we know the point exists. We now just want to know specifically where is it. State here, f of 0 equals 2, and f of 1 equals 1 minus 3 plus 2 plus 2 equals 2. F is a polynomial, so it is continuous on 0, 1, and f is a polynomial. So it is differentiable on 0, 1 via the power rule. This implies Rolle's theorem of mean value. This is the how you know. that being said, we know there is a c in the interval 0, 1 such that f prime of c should be equal to 0. So all we're going to do is we're going to find the derivative, f prime of x is 3x squared minus 6x plus 2. It's a polynomial, so it shouldn't be too much trouble to differentiate. This implies that f prime of c would be 3c squared minus 6c plus 2. And we want that value equals 0. How do you solve that?
Quadratic formula.
Sure. Does it factor?
Probably.
I'd probably check factoring first.
I just do quadratic.
Let's see. It would have to be 2 and 1, right? So 2 and 1, that'll be 5, 2, and 1. Yeah, it actually doesn't factor. So quadratic formula. This implies your c is equal to minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. This is going to be 24 here.
Mm-hmm.
So 36 minus 24. What is that, 12? So that's 6 plus or minus, that's 4 times 3, so this is 2 rad 3 all over 6. And so I get 1 plus or minus radical 3 over 3. Let's continue over here. So what's the answer?
One minus radical 3 over 3.
Right, the positive one doesn't work. So we have c equals 1 plus radical 3 over 3. This is not in the interval 0, 1, so we reject. That's not a part of the answer. However, c equals 1 minus radical 3 over 3. Okay, so 3 is larger than radical 3 over 3, so this fraction is smaller than 1. So I took 1 minus something smaller than 1, so this is definitely larger than 0. And so that is in the interval. This means c equals 1 minus rad 3 over 3 satisfies the conclusion. Yeah, so a problem like this shouldn't be too difficult. It's really just testing whether you know the theorem. It's not going to be some crazy function usually. It's usually going to be a polynomial and something where you have to apply a quadratic formula or something equally silly. For B, the mean value theorem only requires 2 conditions, and the polynomial will fit both of them. Just here now we're looking at minus 1. Any question on the Rolle's example? I know we're going a little bit fast, but like based on the things that we have done so far, this shouldn't be too hard, I don't think. We've talked about limits and derivatives of all these crazy functions. Differentiating polynomials and solving quadratics should be like, eh. So, because these two I know, and the T applies. So there has to be a point in the open interval that the instantaneous rate of change is going to be equal to the average rate of change. So this implies f prime of c is going to be equal to f of 1. Well, f of 1 is going to be what? F minus c is minus 6 plus 2. Is that 3?
Yeah.
Minus f of minus 1. Okay, so that's going to be 6 plus 4, that's 10 minus 1, is that 9? So that'll be minus 6 over 2, so that's minus 3. And f prime of c would be 3c squared minus 4c minus 4. Does this one factor? Has to be 1 and 1. That would give you a minus 4 middle term, but it gives me a positive 1 somehow. Quadratic formula again. Minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. That's 16 plus 12. That's 28. 4 embedded is 2 12. I factored out a common 4 here. The radical of 4 is the 2. I'd be left with a 4 plus 3. So this is 2/3 plus or minus radical 7. And I think both of those work.
Addition doesn't.
The addition doesn't?
No, you get 1.5.
Rejected. That's kind of it. So, I mean, as far as test questions go, it won't be that difficult a time dealing with either of these theorems, but they are super important outside of the test. We'll stop there, and we'll see you guys in, not next week, 2 Tuesdays from now. I know you'll all spend that time studying. You're such nice students.